In this section, section 7.3, we're looking at using similar right triangles. So before we get to our first theorem, let's just look at the typical diagram we're going to see today. And that's going to be a right triangle where we have an altitude drawn, and that's CD. And in that right triangle with the altitude, we're then given actually two new right triangles. We have this one on the left, and we have this one on the right. So before we get into the theorem and get into these different things we're going to do within solving, let's just say, okay, first they're similar. Our theorem will address that in a minute. Just get used to drawing them separately. So I have the big triangle, which is the whole thing. So that has B, C, A. Let's call the second triangle the left side of this big diagram. And so C, D, A. And this last small triangle is that right piece that we have there, and that would be B, D, C. So this gives us three triangles from this diagram. If we think back to last chapter with similarity, if I have that these three objects are similar, I can solve problems with proportions for values I don't need. This is the foundation for what we need to do with this section. If all else fails, go back to this type of problem, set up three triangles, label what you know, and try to find a proportion. That will kind of be your backup plan for this. So let's continue. Our first theorem we have is theorem 7.5, and it kind of addresses what we just said. If the altitude is drawn to the hypotenuse of a right triangle, that's here, then the two triangles formed are similar to the original triangle and to each other. So if I have this, then I know that CBD, let's number these out with that 1, 2, and 3. CBD is similar to ABC, so 3 is similar to 1. ACD, 2, is similar to ABC, which is 1. And CBD, which is 3, is similar to ACD, which is 2. So 1 and 3 are similar, 2 and 1 is similar, and 3 and 2 are similar. In other words, they're all similar to each other. We could pick two of them at a time, set up a proportion, and solve. So what we're going to solve, let's look at our next one here. I have the same diagram as before. ACB has an altitude CD, but now I have values. So let's copy in those letters I just had. I had B, C, A, C, D, A, and B, D, C. All right, triangles. Okay, so I have 12, 5, 13. I'm going to solve for the rest of these parts. So CD, AD, BD. Just to make them a little nicer, I'm going to call this X, Y, and Z, so I don't have to refer to them as multiple letters as I go through. So now I can take all of these values I know and assign them to each triangle. So for example, our big triangle, we have 5, 13, and 12 as sidelines. In our smaller triangle, or the middle one we should say, the one on the left, I have X and Y are legs, 12 is the hypotenuse. And in our small triangle, the one on the right, I have Z is the shortest leg, X is the longer leg, and 5 is the hypotenuse. So now I look at all of these. I could use this triangle and this one to solve for X and Y by setting up a proportion. I could use this triangle and this one to solve for X and Z by setting up proportions. So let's use these two first. So we're going to use triangle BCA is similar to triangle CDA. So I'm going to start comparing sides. 5 over X, 13 over 12, 12 over Y. So from this, I can solve for two of them. I can solve for X first. I'm going to get 13X equals 12 times 5, or 60. And that comes out to be X is 60 over 13, or that's an approximation of about 4.6. I use the same idea for Y. Okay, let's see. I have 13y equals 12 times 12, or 144. That means y equals 144 over 13. So y is approximately 11.1. So far, I know x is 4.6, y is 11.1. Notice these values were a part of this left piece, this left triangle, which I could use with the big triangle to find them. Now, before we find z, we'll use these two to find z. Let's just think for a minute what it could be. I know 13 is the entire length. This is 11.1. So how much is left for z? Well, I'll do some quick subtraction. 13 minus 11.1 is 1.9. So hopefully z comes out to be 1.9. Well, let's find out.
Just a reminder to all teachers to please post your attendance. We're waiting on you. Thank you.
I'm going to compare these two triangles. So I can say 5 over z equals 13 over 5 equals 12 over x. I'm going to use these two to solve for z. I get 13z equals 25, or 5 times 5. Z equals 25 over 13, which comes out to be about 1.9, which is what we found. Now, these numbers weren't real nice, and we'll have nicer numbers at times, not these weird decimals or these big fractions, but it's just that process we have to get used to as we're setting up these triangles and solving to find similarity. Let's look at another one. So now I have EGF and HG is my altitude. If I draw my big triangle first, I have 5, 3, 4. Smaller triangle, I have 3 and x. And the bottom piece here, I get 4 and x. So just by tracing these out, I could identify which ones are similar, but we're just going to find x here. Well, I can compare these two and say 5 over 3 equals 4 over x. Or I can compare these two and say 3 over x equals 5 over 4. Now, if we take a second and look at both of these proportions, if I do the cross product for both of these, they come out to be the same thing. 5x equals 12. And that's because x is going to be the same value in either one. X comes out to be 12 over 5, or 2.4. Doesn't matter which ones I chose, and in a minute we're going to see how we could actually use that with some parts of the hypotenuse, but go back to those proportions, set them up with those similar triangles, and you'll find your values. So, where we're at now is we actually have two theorems, the geometric mean altitude theorem and the geometric mean leg theorem. Both of the theorems start with this setup, which says in a right triangle, the altitude from the right angles to the hypotenuse divides the hypotenuse into two segments. Or this type of setup. I have the altitude, I have AD, I have BD as my parts. That happens in both of them. This one finishes with the length of the altitude is the geometric mean of the length of the two segments. So it's saying this altitude is a geometric mean of these two parts, which we have in the proportion. We're going to look in a minute how to simplify that, make it a little easier. The leg theorem, which I think is a little more complicated, says the length of each leg of a right triangle is the geometric mean of the length of the hypotenuse, so the whole thing, and the segment of the hypotenuse adjacent to the leg. So that would be AD if we were talking about AC. And we have proportions from that. So you may be looking, where are we getting these proportions, and why are we talking about the geometric mean? We've seen geometric mean before, but really it was in the context of just given two numbers. What we're going to use this for is actually just looking at similar triangles. Now, before we get to the way to use similar triangles, let's just look at what these theorems said. It said the geometric mean altitude theorem is the altitude squared equals the segment of the hypotenuse times the other segment of the hypotenuse. Our altitude is CD. One segment we have is AD. The other segment we have is BD. So we're saying here is CD squared equals AD times BD. If we look down at the geometric mean leg theorem, we're saying a leg squared. Realize we have two legs here. We have AC and BC. Let's use AC. I need a hypotenuse and a segment of the hypotenuse next to the leg, which would be AD, not BD. So my leg squared is AC squared equals AB times AD. Now, where are we getting these from? They were from the actual theorem, but let's take a step back and look at the triangles we've been talking about. Let's break these down into similar triangles and see if we can find these and develop these without having to so much memorize these forms, but be able to find them for any form just because we have similar triangles. So this is how we're going to use it. Now, if I look at my altitude theorem, I'm talking about CD, which is my altitude. So I'm going to ask myself the question, what two triangles have CD? So which two triangles in that diagram is CD in? Because if it's in two of them, I can use those two and write a proportion with them. The first one I see is the one on the left. So I go D, C, A, there's CD. The other one I see is the one on the right. I could take this and I could rotate it 90 degrees. Looks like we got the sun coming out. Let's move out of there. Looks like the rainstorm passed. So now we have our triangle on the right here. We have D, B, C. CD is right there. So let's take this and write a proportion using the CDs. So CD matches up with BD. That's a ratio. And that's to AD over CD. There's a ratio. I have my proportion. I look at the cross product, and that is CD squared equals AD times BD. Now, does that look familiar? It should. It's what we just said from the theorem when we said altitude squared equals segment squared times segment squared. Matches up, but now we didn't have to rely on memorizing this. We could just use similar triangles. Okay, let's do the same thing with the leg theorem. Leg theorem, let's pick AC. Realize the legs is AC or BC, but we're going to pick AC. I'm going to ask myself the same question. What two triangles have AC? Well, I have the one that's on the left side with CDA. It's right there. And I have the triangle that's the whole thing. If I rotate that around, C is my hypotenuse, B is at the end of my shorter leg, and A is at the end of my longer leg. There's the other AC. So AC over AB equals AD over AC. Now I look at the cross product. I get AC squared equals AB times AD, which matches what we said before. This would be the leg squared equals the hypotenuse times the segment of the hypotenuse adjacent to the leg, or what we found, but again, we went back and we just set it up using similar triangles, which I think will be an easier way for you. Now, let's take this approach and solve a couple problems. Now, as we go through, we're either going to get an altitude value or a leg value. We're going to have values down here that we're going to use. But it's that altitude or leg value that's going to separate it, and the thing we want to go back to is what triangles can we draw from it. So let's get some basic ones first. What we have here. So I have Z, this entire hypotenuse, 16 is this top part, 27 looks like a leg. So we have a leg there. We're going to use that leg theorem. Now 27 needs to be in two triangles. It is in the triangle that's the whole thing. That would be 27 and Z. It's also in this triangle on the right, which I could draw here. Let's leave in the same direction as it was. We're just kind of rotating it down. 16 and 27. Now, even though they're not facing the same direction, we can match them up. We can go hypotenuse to hypotenuse, z over 27, equals leg to leg, 27 over 16. I can do cross product now. 16z equals 27 times 27. That gives me 16z equals 729. I divide, I get 729 over 16, which comes out to be about, let's see here, about 45.6. Okay, look at the next one. The next one I have x is still a leg. It's in two triangles. It's in the triangle, that's the whole thing. For the triangle, that's the whole thing. This long side is 9. And then I need the triangle, the bottom piece. The hypotenuse here is x. The other side is 5. So hypotenuse to hypotenuse is 9 over x equals x over 5, leg over leg. I get x squared equals 45. X equals the square root of 45. I can simplify that, because that is 9 times 5 to be 3 root 5. And we get, for that one, it's about 6.7. Leaving it in simplified radical form would be perfectly fine and be an acceptable answer. Okay, last one. Now we look at y. Y is now a median. Not a median, an altitude. Got my chapters mixed up. So y is the altitude. Thinking which triangles is y in. It's in this left piece and this right piece. So I'm going to take this one and redraw it, keeping it the same direction. I have 8 and y. And I'm going to take this one and rotate it. So I have y on top, 5 on the side. Now I can match it up. It's 8 over y equals y over 5. That's y squared equals 40. Y equals the square root of 40, which we can simplify because that's 4 times 10, or 4 root 10. Oh, nope, so let's try again. 2 root 10, which we simplify in our calculator to be approximately 6.3. As you go through these, leaving them in simplified radical form would be fine. That's what you should expect for your test. It does say the nearest tenth. We can make the problem happy and give them as that, but as long as you can get to this point, I know the fraction's a little weird. We have the radicals there. Get to that point. That's the key. Okay, lastly, we have a example here. We're looking at a rock climbing wall. So we need to find the cost of installing a rock wall in your school. And you first find the height of the gym wall. So we have this person standing here looking at a corner of a square, and this actually gives him a line of sight to the floor and the ceiling, and he can actually measure from his eye line down, it's 5 feet, and he's 8.5 feet from the wall, which seems like odd measurements, but they actually let you have similar triangles, because I have a right triangle there, to find that W. Now, the picture's a little light, so let's redraw what we actually have here. This is 8.5, and what is it? Hopefully you just said out loud by yourself, sitting there watching the video, that it is an altitude. If you did, good job. If you didn't, pay attention. Okay, so we have an altitude. We need to set up the proportion, and we think to ourselves, what two triangles is that 8.5 in? Not the W so much, because the W is only in one triangle. It's in that top half. But the 8.5 is in the top triangle, and it's in the bottom triangle if we rotate it. Now we can say 8.5 over 5 equals W over 8.5. Gives us 8.5 squared equals 5W. 8.5 squared is 72.25 equals 5W. Divide that by 5. We get 14.45 equals W. So that means the height from this point to the top, or let's say from this point to the top, is 14.45 feet. They want the total height of the gym. So in that case, it's going to be 14.45 plus the height we already have, which is 5, so it's 19.45. That more fits to the problem, but what we need for the similar triangles is getting to that 14.45. So I hope that helps, and good luck on the homework.